Hi, in this problem 2.32, page 80, in this problem we will be dealing with evaluating work. In this problem we are told we have a gas contained within a piston cylinder assembly undergo three processes in series. The first process goes from state 1 to state 2, and this process is a constant volume process, meaning that the volume does not change. From pressure of the gas at state 1 equal 1 bar, and the volume of the gas at state 1 is 4 meter cube, to state 2 where the pressure of the gas at state 2 is equal to 2 bar, and remember it's a constant volume, which means that the volume of the gas at state 2 is the same 4 meter cube. The second process is from state 2 to state 3. This process is compression process. So here the volume will decrease and the pressure will increase, because the increase in pressure will cause decrease in volume. To volume of the gas at state 3 equal 2 meter cube, during which the pressure volume relationship is PV equal constant. So this PV equal constant used to find work in variable pressure systems. When pressure varies during a process, we call it polytropic process. Now, what does constant mean? Now, as we mentioned in the beginning, there is a compression. So as pressure increase, there is a decrease in volume. So the relationship between pressure and volume is inversely proportional. Now, the constant means that change is constant, meaning, for example, let's say that the pressure was increased by, let's say, 1 kilopascal. That increase in pressure by 1 kilopascal decreased the volume by, let's say, 1 millimeter cube. Now, if you applied another 1 kilopascal, it will decrease the volume by another 1 millimeter cube. And that's what we mean by, so this constant, we call it the proportionality constant. In some books, they instead of writing constant or letter C, they use the letter K. Now, in the third process that goes from state 3 to state 4, it tells us that constant pressure so this is a constant pressure isobaric process to state 4, where volume 4 is equal to 1 meter cube. Here we are asked to sketch the process in series on pressure volume coordinates and evaluate the work for each process in kilojoules. The first step, let's write down what is given to us so things will be clear. All right, so here at state 1, we are told that the pressure of the gas at state 1 is 1 bar. Its volume is 4 meter cube. Now for state 2, the pressure at state 2 is equal to 2 bar. Now the volume of the gas at state 2 is 4 bar. Remember, it's a constant volume process, same volume. Now at state 3, we are told that pressure 3 will be determined by this relationship PV equal constant. And the volume of the gas at state 3 is 2 meter cube. Now state 4, the pressure 4 will be the same as pressure 3 because it's a constant pressure process, isobaric process. And we're told that the volume will decrease to 1 meter cube. So here on the top, we have what is given. Now what we will do is we will draw the PV coordinates and sketch it in here. So the vertical line will be the pressure, and as we go up, we increase in pressure. The horizontal is the volume, and as we go from the right to the left, the volume increase. So at state 1, the pressure at state 1 is 1 bar, and that's what we have in here. Now in this case here, what I did is I increased from 0 an increment of zero point 0.5 bar. So 0.5, 1, 1.5, 2, 2.5, etc. And the same thing for volume, 0.5, 1, 1.5, 2, etc. And the volume at state 1 is 4, so this is state 1. Now for state 2, the pressure is 2 bar, right? The volume is 4. So that is state 2. All right, so here we have the process goes from state 1 to state 2, constant volume process, 4 meter cube, from 1 bar to 2 bar. So now we sketched this process. Now let's find the work that this process did. All right, so what is the definition of work? The work from process 1 to 2 is equal to pressure times change in volume. But as you can see from this sketch, there is no change in volume. So the change in volume is 0. Therefore, the work is 0 kilojoules. Now, at state 3, the volume at state 3 is 2 meter cube, and that's what we have in here. And as we mentioned, this state 3, PV equal constant, where V is to the power 1, which tells us this is an isothermal process. And since this is constant of proportionality, the product of pressure times volume for each state will be the same. So that's what we have in here. So here what we will do is we will solve for pressure 3, and then we will plug in the given values and plug this into your calculator, and it will give you the answer of 4 bar. So that will be your state 3. And since the polytropic index, PV to the power 1, means isothermal, and because it is isothermal, the relationship between the pressure and the volume is inversely proportional, so it will not be a linear relationship, it will be a curved relationship. And as you can see, we are going from state 2 to state 3, going from right to the left, toward the left. So that means that we're going to have, because we're going toward the left, it will be negative work. And we will see. Now the work is from state 2 to state 3 is given by this expression. Now from where did we get this expression? In the beginning we said that work is pressure times change in volume, and that's correct. So to find out how we came to this conclusion, you can go to the thermodynamic playlist in this channel to problem 2.27, where the polytropic index is 1, just like this, PV equal constant, where we took the integration of the work, pressure times change in volume, and we replaced the pressure by rewriting this equation where we solve for pressure in here, volume go to the other side, so pressure will be equal to constant over volume. And since this is constant, we can take it out of the integral. So you can see the whole process and on how we did this integration to reach to this conclusion. And I will try to somewhere here to add a link to this problem. So now let's plug in the given values. So now I forget something. Do not forget to change the units. 1 bar is equivalent to 100,000 Pascal, and Pascal is Newton over meter squared. So for example, at pressure at 2, right here is what? Is 2 bars. So it will be 200,000 Pascal. And that's what we did in here. when you plug this into your calculator, it will give you an answer of minus 554.52 kilojoules. And you see it's a negative sign in here. So that tells us what? So that tells us that the surrounding did, so that means the piston did the work on the gas in here. All right. So at state 4, we said the volume is 1, correct? And it's a constant pressure volume, so it's going to stay 4. And the process goes from 3 to 4 to the left-hand side, so that tells us we're going to have a negative work. So here, the work from state 3 to state 4, pressure times change in volume. The pressure is 400,000. Remember, 1 bar is equivalent to 100,000 Pascal. And as you can see, the change in volume is the final volume minus the initial volume. So that will give you a negative answer, negative 400 kilojoules. So this is the sketch, and for each process we found the work for it. Next problem. 2.33. In this problem, we are told that we have a carbon monoxide gas, CO, contained within a piston cylinder assembly undergoes 3 processes in series. The first process from state 1 to state 2 is an expansion from pressure 1 equal 5 bar, and the volume of the carbon monoxide at state 1 is 0.2 meter cube, to the volume of the carbon monoxide at state 2 equal to 1 meter cube. So the volume increased, expansion. So when we have expansion, it means that we have a decrease in pressure, during which the pressure-volume relationship is PV equal constant, just like the previous problem, a polytropic index. Now, the second process is from state 2 to state 3. This process is constant volume heating from state 2 to state 3, where pressure 3 is equal to 5 bar. The third process is 3 back to state 1. It will be constant pressure compression to initial state. Sketch the processes in series on PV coordinates and evaluate the work for each process in kilojoules. Just like what we did in the previous problem, let's write down what we have. So at state 1, the pressure is 5 bar and the volume is 0.2 meter cube. At state 2, the pressure at state 2 will be determined by this polytropic process, or this polytropic expression, PV to the power 1. And since it is to the power 1, it is an isothermal process. And the volume is 1 meter cube. Now at state 3, the pressure 3 is 5 bar and the volume is 1 meter cube. All right, so here we have what is given to us, and in this problem, I will have the piston cylinder assembly and try to view this process or this cycle using this piston cylinder assembly, so it will be visually so you can understand the concept visually. All right, so at state 1, we are told the pressure is 5 bar and the volume is 0.2 meter cube. So that means this is our state 1. These are the measurable characteristics of the carbon monoxide gas at state 1. So this is right here is a state 1. So these carbon monoxide gas molecules, they are at pressure 5 bar, and the volume that it takes inside the piston cylinder assembly is 0.2 meter cube. Now, state 2 tells us that the volume at state 2 is 1 meter cube. That's what we have in here, right? Now, we want to find what is the pressure at state 2. Now we are told that it is a polytropic process with an index 1, which means it is isothermal, meaning that as the pressure decrease, you can imagine that we have a weight on top of the cylinder, and this weight is divided into different increments. As we remove these increments, in other words, decrease the pressure of the piston on gas, the gas starts to expand. So as you can see, the process is inversely proportional in here. And just like what we did in the previous problem, we will you since the the decrease of pressure versus increase in volume is constant, mean its proportionality is constant, we can use this expression and we can solve for pressure at 2, plug in the given values. So that gives us that pressure 2 is 1 and the volume is 1 bar and the volume is 1 meter cube. So that will be our state 2. And it will be curved like this and it goes to the right. So that tells us we're going to have positive work. Now think about it. The gas in here, it moved the piston up. So the gas, which is in this case the system did work on the surrounding, and here the surrounding is the piston, and the key word here is the gas was able to move the piston from one location to another. So that is why, so when the system, in this case the gas is the system, uh, do work on its surrounding, like the piston, this is called a positive work. Next, we want to find the work value associated with this process. Just like the previous problem, you can go to problem 2.27 on the thermodynamic playlist, and you can see how we got this work expression. So here we plug in the given values, and remember 1 bar is equivalent to 100,000 bar. So here we have 5 bars, so that will be 500,000. We plug in the values, we plug it into our calculator, and it will give us 160.94 kilojoules. So that is how much work the gas did to move the piston from one location to another. Now, in the second process, it tells us that we will have a constant volume where the pressure increase. And it tells us that we introduced heating. And that's what we did in here. So in here, the pressure is 1 bar. We increase the pressure by adding heat instead of applying the piston pressure on the gas. Instead, we add heat to increase the pressure back to 5 bar. And that's what we did for until we reach state 3. It goes back to 5 bar. That pressure increased because we introduced heat. And remember, what we did in this process, that we hold the volume of the gas constant. The volume of the gas didn't change. We were able to change the pressure by increasing the temperature. So when you increase the temperature, you increase the pressure. If you decrease the temperature, you decrease the pressure. All right, so right here, the process goes from state 2 to state 3. Question: what is the work for process 2 to 3? Now let's take a look at the sketch. When we introduced heat to the gas molecules, and the gas molecules pressure increased to 5 bar, Did we move the piston? No, we didn't move anything. There is no change in volume. We didn't move the piston. It means, just like the previous problem, a constant volume process will give you zero work. So now we will go back from 3 back to 1. And as you can see, this work goes from the right to the left, so toward the left direction. So it will be negative work. So now what's happening is we are, when the gas reached to 5 bars, we applied a pressure from the gas, a constant pressure from the piston on the gas to take it back to its original volume of zero point 0.2. So now let's find the work from pressure from state 3 to state 1. So it will be pressure times change in volume. Pressure is 500,000 Newton over meter squared, and that's the change in volume. The final volume minus the initial volume, and that will give us a negative 400 kilojoules. So that's how much work the piston need to do in order to take the gas molecules with a 5 bar pressure back to its original volume of 0.2 meter cube. Thank you very much. Have a good day.